The first speaker is HLadreyt. She is a PhD candidate at ANSYS in France and CERAD in Cambodia. Today, she will be talking about how can a multi-host system become a maintenance community for Japanese encephalitis virus transmission in a Cambodian village. Please, Elena, the floor is yours. I think you are muted, Elena.
Sorry for the little mistake. I'm here. Sorry. Thank you very much. So thank you for introducing me. Yes, so today I will present you a work. Sorry, the title changed a little bit since the abstract. A work on modeling Japanese encephalitis virus transmission dynamics and human exposure in a Cambodian rural multi-host system, which is a work with my PhD supervisor, Véronique Chevalier and Benoît Durand. So Japanese encephalitis is a serious vector-borne zoonosis caused by a flavivirus. It's the main cause of acute encephalitis in Asia, especially in children, But figures in clinical incidence are believed to be underestimated.
Yeah.
You can see my
Oh, we can't see your slides.
Okay, what's happening?
Sorry. Yeah, now it's on.
Okay, sorry for the mistake. I don't know what happened. You can see them now, okay?
Yeah.
Yes.
Okay, sorry.
No worries.
Back, check. So as I was saying, the figures of clinical incidence of Japanese encephalitis are believed to be underestimated because of underdiagnosis and cross-reactions of tests with other flaviviruses as dengue virus. GEV, Japanese encephalitis, is found throughout all Southeast Asia, but has spread to Northern Australia, and an indigenous case was confirmed in Angola in 2017. A vaccine does exist, but only half of the concerned countries has implemented vaccination programs, and the epidemiological cycle is complex and still partially understood. So this is the traditionally described cycle, which implicates wild birds as reservoir, domestic pigs as the main amplifying host, and collects mosquitoes as vectors. Humans, horse, and other mammals as cattle and dogs are dead-end host or non-competent host, which means that they are exposed to the virus, but they do not develop a high viremia enough to infect back mosquitoes feeding on them. So wild birds are often considered to be the main reservoir, but very few recent studies are available. And in addition, GEV circulates within areas with very low density of wild birds, but also low density of pigs, suggesting that secondary reservoirs might be implicated in these regions. On the other hand, poultry is exposed to GEV, especially in Cambodia, and shown experimentally able to reinfect mosquitoes. So in Cambodia, GEV circulates widely in humans, but the infection is underdetected and the level of exposure is very difficult to estimate. GEV circulates in low pigs and wild birds density areas in Cambodia, and poultry have been shown to be exposed to GEV. So then GEV could be maintained in a more complex or multi-host system with at least pigs and poultry as competent hosts, and cattle, dogs, and humans as non-competent hosts, this being the populations found in traditional villages. However, epidemiological systems are bound to change for political, cultural, and sanitary reasons, for example, with ASF outbreaks in Asia, which could affect GEV transmission dynamics. So the objectives of this study were to model GEV transmission in a rural multi-host system in Cambodia, to analyze how the relative abundance of each host affects the ability of this system to sustain GEV transmission, and then to assess and characterize the human exposure to GEV infection in the study area. To achieve these goals, we developed a deterministic compartmental model that we calibrated using field and literature data. Then we used this model to calculate R0 and assess the level of human infection in a traditional Cambodian village, as well as to predict the variations of these indicators according to the composition of the multi-host system. So the study focuses on 3 districts of Kendal province, which is around Phnom Penh. We led a serological survey to assess the relative exposure to GEV of several species constituting this multi-host system, so pigs, poultry, and dogs. We also collected demographic data to calculate host population sizes in a traditional village here. And the samples were analyzed by the virology unit of Institut Pasteur du Cambodge. So we chose to implement a deterministic model because the vector population is large, is known to be large, and the level of GEV circulation in the study area is high in the all year. We assumed that hosts were exposed to a single vector population, collect species, and the backyard breeding system in Kendal province made us assume that all hosts were homogeneously exposed to the vector population, and so we structured host population by village and not by household. We did not represent movement of animals between villages because they are known to be very rare, and host population size were assumed to be constant with birth offsetting deaths. And finally, we also considered that vector population was constant as we were focusing on a small study area where the seasonality of GEV circulation is low and where vector abundance is high all year round. So the model describes local transmission of GEV between competent hosts, pigs, sows, ducks, and chickens, and vector, collect species, and 2 non-competent hosts, so humans, dogs, and cows. The different health states of the host and vectors are represented here, with M protected by their maternal immunity, S for susceptible, E for latent, infected but not infectious, I for infected and infectious, and R for recovered. So as you see, all the vectors emerge sensitive, susceptible, and stay infectious until their death. The force of infection is the instantaneous probability to become infected and depend on several parameters here listed. And in addition, for non-competent hosts, the force of infection for vectors here will be 0 because they cannot infect back mosquitoes. The epidemiological entity is the village here with the population sizes coming from the field data. And these are the input parameters for the model that we set from literature and field data. And in particular, these are the feeding preferences, which is the fact that a vector prefers to take its blood meal in a particular host. So this data came from a field study carried out in Kendal province, so in the same study area. And here are the values relatively to pigs. As you see, pigs feeding preference is 1. So we needed to estimate the 2 missing feeding preferences for dogs and ducks, but also the size of the vector population that is active in GEV transmission that we called NV, which is something that we cannot observe on the field. So for parameter estimation, we used the serological data I presented you before. As GE is endemic in Cambodia, these seroprevalence rates are assumed to correspond to the epidemiological equilibrium of the system. Then the model predicts for a given value of the vector of the 3 parameters, seroprevalence rates per species and per district. Then we use the NLM function that minimizes the log likelihood of the observed seroprevalence conditionally to the predicted ones. We had 4 output variables. So first the R0, the basic reproduction number. Then at the epidemiological equilibrium, the model calculated the annual probability of human exposure to GEV, which corresponds to the probability of receiving at least 1 infectious bite in 1 year. Then it calculated the average age at infection of humans and the annual incidence rate. We calculated this indicator for the modeled village, which correspond to the observed situation on the field. Then we made vary this system composition. But to make the different scenario comparable, a constant vector population has to be used. Since the vector population is assumed to depend on the body surface area available for biting, body surface area or BSA, a constant overall village BSA was kept. Within this constant village BSA, the abundance of each host was then varied by changing the relative proportion of BSA within the total village BSA. And individual BSA per species were calculated with allometric formulas. I will present 2 scenarios. So first, we varied the proportion of non-competent hosts against competent hosts. And then we varied the relative proportion of pigs, chickens, and ducks among competent hosts, so pigs, chicken, and ducks, in order to clarify their relative importance in GEV transmission. Then we observe the impact of this variation on the 4 indicators. So here are the estimated parameters and the calculated indicators in the observed situation, In the model village, R0 was around 1.3. The annual incidence rate was around 14 per 1,000 people, corresponding in our village to around 47 infections per year. And the average age at infection was very low, around 2 years old. When changing the composition of the system, and here modifying the relative abundance of hosts against competent hosts against non-competent hosts, we observed that R0 exceeded 1 when there were more than 15% of competent hosts in the system. The dashed line in the middle is the observed situation, and the dotted lines here represent 2 scenarios. In scenario A here, with 15% of competent hosts, a low exposure probability, here in blue, was associated with a high average age at infection, around 40 years old. In scenario B, however, which is similar to the observed situation, yes, we observed a high probability of human exposure, but very low average age at infection. This means that the infection here are concentrated in the younger age groups. Then, to vary the 3 BSAs of pigs, chicken, and ducks, we set the proportion of chickens in poultry at 5, in terms of BSA, at 5, 55, and 95%. Then we varied the proportion of pigs among the 3 competent hosts here. R0 was mainly influenced by the proportion of pigs in the system. As you can see here, it increased almost linearly, whatever the scenario. Then in scenario A, with 5% of chicken and poultry, R0 exceeded 1 when there were more than 30% of pigs in the system, here. But in scenario B, where there were more chickens, R0 exceeded 1 with only 10% of pigs in the system. So here we have first an increase of R0 with the quantity of chickens, because chickens have shorter lifespan than ducks, 6 months against 2 years, which ensures a faster turnover of susceptible and competent animals in the system. But when chickens becomes the majority in the competent host, like scenario C, then the intensity of transmission decreases. It takes more than 35% of pigs in the system for the R0 to exceed 1. This is due to the fact that the feeding preference of culex for chickens was the lowest of all species. So when there are almost only chickens among the 3 competent hosts, the vector will preferentially go to feed on non-competent hosts, and thus the intensity of transmission will decrease. A second observation was that the confidence interval of the R0 in scenario B included 1 when there were 0 pigs in the system. This suggests that GEV could circulate without pigs. Finally, we got the same result, same conclusion as before, with in these right parts of the graph, a high exposition, proportion of exposition of human correlated with a very low average age at infection, and so a concentration of the infection in the younger age groups. So finally, in the observed situation, which was a traditional rural village of Kendal province, the model estimated around 47 infections per village per year. We tried to go a little further by wondering what might be a rough estimation of clinical cases, as not all infections are symptomatic. Some authors estimated that 1/500 to 1/250 infections resulted in clinical cases. So we applied these ratios to the incidence we calculated with the model, and we roughly estimated a clinical incidence of 3 to 6/100,000 clinical GEV cases per year. These figures are consistent with the literature, even if the published data is essentially based on data from hospital where acute encephalitis syndrome is diagnosed, and so might underestimate the global incidence. Then the average age at infection we estimated was very low in our modeled village, but we know that children are more subjected to serious form of the infection and to severe sequelae, so this result clearly underlines the need to vaccinate children in Cambodia. But as a limit, our model did not structure people in age group, so it considered that children were as exposed as adults while they have a much lower body surface area. So we are overestimated children exposition to GEV infections. Quickly, the model then predicted different patterns of age at infection. So in what we could call intermediate area with few pigs or few competent hosts, as in peri-urban areas, the exposure probability was low and the average age at infection was high, and we can expect a lower burden on human health. On the contrary, in the scenario with more pigs or just more competent hosts as rural areas, the exposure probability was high, but the age at infection was very low. So here, a higher burden on human health might be expected. The study confirmed the major role played by pigs in GEV transmission. However, we saw that in a system with no pigs, poultry might act as a secondary reservoir. And then we underlined here the importance of using a global approach to study this vector-borne zoonosis by considering a multi-host system or maintenance community. The scenarios we have considered are likely to occur in the current sanitary context related to the circulation of ASF in Asia is a concrete example of these changes. For example, in Vietnam, more than 20% of the total pig herd was decimated in 2020, but the reduction of the total number of pigs herd due to ASF has led to a rapid growth of cattle and poultry production. And the industrialization of the pig sector is causing the disappearance of small farmers and pigs in backyards. And on the other hand, landscape management linked to industrialization as well as climate change could also transform the epidemiological system by directly affecting host and vector population, and thus the transmission pattern of GEV. Finally, it's not a result that I presented you, but the model also showed that GEV seroprevalence in dogs, which are numerous and live in close contact with humans, could be a good proxy for human exposure, which is more difficult to observe in the field. Thank you very much for listening to me. Sorry to be a little too long, and I would like to thank ModAH committee a lot and the many people who contributed greatly in the project.
Thank you, Elena. Thank you for a very nice talk. Do we have any questions in the audience? So Egil had one question, but no, I forgot it was answered. Emmanuel, do you have any question?
Yes, I have a question. It's a very nice model because it's a well, it's not really simple, but it's relatively simple, and it can be very useful. I had a question because you said that it's a collects species, but you didn't mention if there are several species. And if you know that, do you know if you can have several species, and if you have several species, probably they will have different preferences. And this can be a mechanism where you limit the contact between hosts, because each collex has its own preferences. And I was thinking it can be a case where diversity, and so biodiversity can be a fence to transmission between species. It would be great.
Yeah, exactly. So the main described vector is Culex tritaeniorhynchus, but many other species of Culex have been shown to be competent for GEV, as Kinke fasciatus and Vishni. In Cambodia, the main vector, the more abundant is tritaeniorhynchus. But we considered one vector, Culex vector population, because we had data. We know that Kinke fasciatus and also Vishni, which are very numerous in Cambodia, we had information of feeding preferences on these 3 different species. So there were a study from Boyer and Al in 2021 that had the information for each species, but also all the Culex together. So we chose to simplify more or less by representing just one population of Culex species, but exactly. And also 3 studies showed that some IDES vectors might be also competent, but in laboratory conditions. Anyway, it's a laboratory condition all the time, but so this also asks a new question about interaction between host and vector, and maybe in other regions where there are more IDES, for example, IDES albopictus, and will they be able to transmit and maintain the circulation of GEV in case of this introduction?
Okay, thank you. So you know how to go with your model now.
Yes, the next step.
Thank you, Elena. Thank you again for a very nice talk. I don't think we have time for more questions, but need to move on to the next speaker.